Well, hi everyone. Let's have this video to help you with a review of the renal system or the urinary system, which we did cover in our lectures at the FGCU. We're going to focus today on the main parts of this chapter, which I want you to concentrate on during your review, which is the glomerular filtration and the regulation of the glomerular filtration, the renin, angiotensin, vasopressin mechanisms, the reabsorption, the renal reabsorption, which is happening in the tubular part. And then finally we will talk about the renal excretion or the urinary excretion of the molecules that you don't want to be retained in your system. When we are discussing together in this video the renal reabsorption, we will pay special attention to something we covered together at the lectures. We call that the counter current multiplication, which occurs at the loop of Henle, and how the loop of Henle in particular in the juxtamedullary nephrons can produce concentrated urine using this counter current multiplication phenomena that we see in the kidney. So with this kind of introduction, let's go through what we already covered at the lectures in a quick review to remind you and hopefully to help you in the final stretch in understanding and remembering the issues and the topics we discussed together during the lecture. So the urinary system we discussed together, you have the two kidneys, one on each side, and they're very close to the posterior abdominal wall, and therefore many of the surgeries are performed from the back, not from the front of the abdomen. Above the kidneys you will have small glands, pyramidal glands here. We call those the suprarenal glands or the adrenal glands. The kidneys are surrounded by fat, and in addition to giving you the support you need, as we all know, fat can be consumed for energy, and that's precisely what the kidneys do. In case you don't have enough glucose, the kidneys will start utilizing the perirenal fat, which is very heavy around the kidneys, and for the reason I just mentioned. We'll realize from this diagram, from this picture, the drawing here, that the left kidney is slightly higher than the right kidney, and we will also realize that the renal artery is emerging straight from the aorta, from the abdominal aorta. And you will see, because the abdominal aorta is slightly on the left side, you will see that the renal artery is shorter on the left side than it is on the right side. From the kidney, we will have over here what we call the kidney pelvis, which is a cavity inside the kidney that will drain into the ureter, and from the ureter you're entering the urinary bladder. And from the urinary bladder you will have the urethra that empties the formed urine outside. Okay. The main kidney functions would be to maintain the stability of your extracellular fluid, the electrolyte composition, the osmolarity. When you're drinking a lot of water, this water has to go somewhere. And when you're not drinking enough water, you don't want to produce too much urine, because you will easily get into dehydration. But water is not the only thing. We need to get rid of sodium. We need to maintain sodium and get rid of the excess of sodium. we need to get rid of the excessive amount of potassium that we don't need in our system. We need to get rid of urea and other metabolic waste products. We don't really want to accumulate in our system hormones that have already expired and did their work, and they're conjugated now into water soluble molecule, and you want that out. That will be also the function of your kidneys. Kidneys are very important in maintaining your electrolyte balance and also your pH balance. As we will study together in the next chapter, the kidneys help in excreting hydrogen ion, and they also help in modulating the concentration of the carbonate in your system, and we will talk about that when we get in, especially to our next chapter. Okay, so other random functions or miscellaneous functions for the kidneys. It does maintain the water balance, the osmolarity of the extracellular fluid, the waste products. It eliminates the waste from your bodily metabolism. It has some hormone activities, so it functions as an endocrine organ. It produces a hormone called erythropoietin, which helps you produce more red blood cells from your bone marrow as needed in response to hypoxia, renal hypoxia. It produces renin, which is an enzyme that will help you cleaving a hormone called angiotensinogen into angiotensin 1. And we will see that later on during our review. It helps also in converting vitamin D from its precursor shape into the active form. Therefore, it helps in regulating your calcium level, both indirectly by manipulating vitamin D, which will help you absorbing more calcium from your intestine, and also would regulate the levels that you're excreting from calcium and phosphate when we get into the tubular reabsorption or the renal tubules. So anatomically, we didn't focus much on it at the lecture, neither that we will do now. But like I said in my introduction, that you do have the kidneys and the ureters that are emerging from each of the kidneys, and that they empty to the urinary bladder, and that will empty to the urethra. Of course, we do have some abnormalities. We have abnormalities in the shape of the kidneys. Sometimes the two kidneys are not separated from each other. They form a structure called horseshoe kidneys. Sometimes you have more than two kidneys. Sometimes you don't have except one kidney, and the other one has atrophied, or it never even went into full development. So we do have abnormalities. It can be also in the form of too tight ureters, and which will cause retrograde pressure on the kidneys, and that of course can lead to serious diseases. We have diseases that will make cysts inside the kidneys. Unfortunately, that's a common disease, and we call that polycystic kidney, and that can result in, if it's severe enough, it can result in significant damage to the kidney. So what I'm trying to say is, what you're learning in this class is the classical way and the classical anatomy and the physiology, the normal anatomy and the physiology. And of course there are many things that can go wrong during development and later on in life. So if we cut through the kidney, and I want you to remember this part here, that the outside of the kidney, we'll call that the cortex, and the inside part we'll call the medulla, and we agreed that this is the pelvis of the kidney, the renal pelvis, and from which the ureter does emerge. The important aspect of dividing the kidney into cortex and medulla, as we will realize later on, that the osmotic pressure of the medulla goes higher as you go deeper and deeper into the medulla and away from the renal cortex. We will also learn that we have two kinds of nephrons. This is a nephron here, which is the functional unit of your kidneys. And we have nephrons that are mainly located in the cortex, and we have nephrons that start very close to the medulla and they dip very, very deep into the medulla. We call them juxtamedullary nephrons. And we'll talk about each of those later on. Okay. I'm going to avoid the anatomy of the kidney since this is pure physiology class. So let's go ahead and skip through the anatomy, but these aspects are available for you if you are interested to read from the slides I posted on your Angel website. The urethra, one thing I like to mention here is that the fact that the urethra is fairly shorter and wider and straighter in female than in males, and that of course causes urinary tract infection to be more common in the female. Also the proximity, because between the urethral orifice and the anal orifice allows the bacteria to get into the urethra, which is not exactly the case in male. All right, the nephron, now we are getting into the important aspect of our lecture. The nephron is the functional unit of our kidneys, and we have two components. We have the vascular component, which is essentially a tuft of capillaries that are wrapped around, and we have what we call the afferent arteriole and the efferent arteriole. Afferent arteriole will be carrying the blood toward that nephron, toward that glomerular tuft of capillaries, and the efferent is carrying the blood away from it. Now that's not the only blood we are concerned about. There are a lot of blood vessels and capillaries that are surrounding the tubules, and their function is to uptake everything that the tubules are reabsorbing, to make sure that the interstitial space is not swelling, and also to make sure that you are maintaining the steady flow of things you need to absorb from the tubules, from the lumen of the tubules into the interstitial space. And as we had discussed previously, if you are not taking away whatever you are dumping into the interstitial space, quite soon you will reach equilibrium for the diffusion or the pumping mechanisms, and that will make it very hard for you to reabsorb anything. And so these blood vessels are situated, whether they are the peritubular capillaries or the vasa recta, and we will talk about each of them in the next couple of slides. But they perform very important functions in maintaining the osmotic pressure of your interstitial space in the kidneys, and therefore they allow themselves to contribute in the formation of urine by forming concentrated or diluted urine as needed. And we will talk about them in particular when we come to the vasa recta. So this is the classical nephron, which is, in this case, this is 80% of the nephrons look like this, which is the cortical nephron. What you will see is that we have the vascular part, which will be, as I said earlier, the glomerular tuft of capillaries here, which is fed by an afferent arteriole and is drained away by an efferent arteriole. We also agreed that the efferent arteriole is significantly less in the diameter than the afferent arteriole. Now, the efferent arteriole is going to branch up and give you all those capillaries, the peritubular capillaries that are surrounding the tubules, and this, what you see here, is the vascular component of your kidneys, now of your nephron. Now, when it comes to the juxtamedullary nephron, you will realize that we have an additional component, which is the vasa recta, that's important for the function of the kidneys, and we'll talk about that component when we get to it. In addition to the vascular component, we do have the tubular component, which starts here at the Bowman capsule, which will funnel all the liquid that is getting filtrated from the glomerular capillaries and lead it to what we call the proximal convoluted tubule. Now, the proximal convoluted tubule is much more complicated than this. It's really forming many more loops and convolution, and hence the name, the proximal convoluted tubule. That will lead into the loop of Henle, and the loop of Henle has two distinguishing components, both functionally and histologically. We call them the descending limb, or the thin segment, and the ascending limb, which will be the thick segment, and they do function relatively different from each other. From there, we will lead ourselves into the distal convoluted tubule, and you will see that the distal convoluted tubule will make sure to cross between the afferent and the efferent arteriole, as we discussed in our lecture, to produce to you what we call the macula densa, which are modified cells at this part here of the distal convoluted tubule, and that part is responsive to high sodium in the filtrate, and therefore it will start paracrine stimulation of those structures surrounding it, which is very, very important part. We call this component collectively, that includes the macula densa, the afferent arteriole, and the mesangial cells and the juxtaglomerular cells, or the granular cells. We call that juxtaglomerular apparatus. That's an important word, and we're going to spend quite a good amount of time talking about the juxtaglomerular apparatus in this review. So, as I said earlier, the nephron has the vascular component, which is the dominant part of the glomerulus. It has a ball-like tuft of capillaries, and the water and all the solutes that are small enough would be passing through the glomerulus, and we call that the glomerular filtrate. Well, what causes the glomerular filtrate to form is very specific structures that are unique to the glomerular anatomy or microanatomy. What we will realize, if I would to skip this picture here, is let's go to the structure of the glomerular capillaries, and then I will get back to it. To the early slides. What's unique about the vascular component here, as we discussed during the lectures, is the fact that the afferent arteriole is wider than the efferent arteriole, and that creates quite high pressure inside here. In addition to it, the lining of the endothelial capillaries, the endothelial of the capillaries by the endothelial cells, they have holes in it, and we call them fenestrated endothelium. That allows molecules to pass through only if they are within a specific range. And in addition, you have a very thin basement membrane, and that basement membrane will allow things also to pass through, since it's very thin. But it also has a negative charge, which is capable, therefore, of repelling negatively charged proteins. Finally, the parietal layer of, or the visceral layer, of your Bowman capsule is formed by what we call podocytes, which are cells not really tight to the capillary wall, and it's forming feet surrounding it, and those feet are not even close to each other, and between the feet of those podocytes, we call these guys filtration slits. All of this will result in the fact that the glomerular filtrate, or whatever you have here, will find a very easy access to collect itself into the Bowman capsule. So if we go back to our lectures, and we did agree that the tubular component will have the Bowman capsule, but then we'll also have the proximal convoluted tubule, the loop of Henle, which I showed you earlier that it has significantly different structures in the ascending and the descending limb. They look different, they function different, they have different cell lining of those two limbs of the same loop of Henle, and sometimes we call it the nephron loop. We talked about the juxtaglomerular apparatus quickly, but we're going to spend significant amount of time talking about it. Then we have the distal convoluted tubule, and finally, which is also part of the nephron, we have the collecting duct or the collecting tubules. We'll talk about them. As I said earlier, the nephrons have two types. One of them is located in the cortex of the kidney, and that will be the main type, which is 80% of your nephrons, what we call cortical nephrons. The other guy is called juxtamedullary, next to the medulla, and those guys will be about 15 to 20%, and they serve an important function in their ability to formulate or form concentrated urine when you haven't been drinking enough water, or you want to retain the blood volume, like in case of hemorrhage or in case of shock, where you don't want your body to get rid of additional volume of your water and electrolytes. We'll talk about this function later on, but for now let's just appreciate and understand the fact that we have two types of nephrons. One of them is inside the cortex, and it's closer to the surface of the kidneys. We call them the cortical nephrons, and the other one, which is only 20% or 15%, we call these guys juxtamedullary nephrons. So here is a quick comparison between the cortical nephrons and the juxtamedullary nephrons. Here is the medulla, and you can see how close the nephron is to the medulla. What you realize is the loop of Henle dips really deep towards close to the end of the medulla, and you will realize later on that as you go deeper and deeper into the medulla, the osmotic pressure is increasing, and therefore you are absorbing more and more water from that filtrate, and therefore you are forming highly concentrated urine using those specifically or strategically located loop of Henle's or nephrons collectively. What's important, and also this is one of the things I mentioned earlier, but now you see it illustrated to you in these drawings, is the fact that the nephron on the right, you will see it having what we call vasa recta, and the vasa recta are a group of blood vessels dipping from the efferent arteriole going all the way down, but they get some collaterals from elsewhere, and they dip really deep in, and that's also will help you, the vasa recta will help you in making this concentrated urine, as you will see later on, especially when we talk about the counter current multiplication and the role of the blood vessels in the counter current multiplication. So here's another comparison one more time between the cortical nephron and the juxtamedullary nephron. The renal process can be summarized really into three steps: glomerular filtration, tubular reabsorption, and tubular secretion. That's what we're going to focus on, in addition to some mechanisms and the hormonal mechanisms of antidiuretic hormone, which we call vasopressin, or the renin-angiotensin aldosterone mechanisms. And these will be specialized topics that we will cover together in this lecture. But I want you to understand that the kidney is functioning through those three. Any problem or disturbance of any of those three will result in severe inadequacy of the renal functions and resulting in a phenomena we called renal failure. So the renal failure can really result from any of those three because it's not just one function. It's not like the heart pumping certain amount of blood, and if it doesn't, we will call that heart failure. Here, any failure at any of those three levels will result in significant disturbance of whether the water, the electrolyte, or the ability of your body to excrete the material that you have to excrete out of your body. So let's start with the glomerular filtration. As I explained to you earlier when we looked at the diagram, and we will revisit that diagram again, the fact that the glomerular filtration is taking place is guided by many factors, and some of them are physical and some of them are anatomical. The pressure inside the capillaries is high. As you learned in the cardiovascular system, when you increase the pressure inside the capillaries, you will increase the hydrostatic pressure, and therefore the filtration or the effusion of the fluid from the blood capillaries will go into the interstitial space and resulting in edema, for example. The same thing is happening here. We have extremely high pressure inside the capillaries, unusually high pressure, which is close to 60 millimeter mercury. And we also have a fairly compromised barrier to hold on to the solutions or to the liquid and the electrolytes that are inside the capillaries. And as I explained to you earlier, the fact that we have fenestered endothelium, the fact that we have very thin layer of basement membrane, which has a negative charge, and yes, it's capable of repelling some big proteins, but it will allow, because it's very thin basement membrane, very thin interstitial space, it will allow almost free passage of everything that's small enough. Water, electrolytes, glucose, amino acids, all of these guys will have free access from the capillary lumen into the interstitial space, and then from there into the lumen of the tubules as it starts at the Bowman capsule. Add to it the fact that we have the podocytes, and the podocytes are incomplete coverage of the capillaries at that point, which is the visceral layer of the Bowman capsule. It's supposed to be surrounding the capillaries, but it's not doing a good job in doing so. It's almost like a starfish or an octopus sitting on a rock. So it's leaky from everywhere, and that allows the fluid to pass from underneath and between the feet of these podocytes in what we call earlier the filtration slits. So the glomerular filtration, which is formed here at the glomerulus, is huge amount, as we described during our lectures. We have approximately 180 liter of glomerular filtrate being formed at this level, and it will be the function of the tubules to reabsorb not only the water that you lost, but also the electrolytes and the sugar, the glucose, the amino acids, the proteins that escaped, the calcium, most of the potassium, the bicarbonate, And that's a very important function of the tubules later on in bringing back everything you lost at the glomerular capillaries. Remember, the gaps at the glomerular capillaries are small enough to allow everything to go through except big proteins. Every now and then you have some proteins which are also retaken later on by phagocytosis, or endocytosis rather, not phagocytosis, and we will describe those functions later on. So the glomerular filtrate is fairly large amount of fluid and filtrate that will resemble very much the plasma, except for the fact that it doesn't have enough proteins, and it will be the function of your distal tubules and the loop of Henle and the proximal convoluted tubules and the collecting duct to pick up the matters that you lost and the matters that you need for your body functions. As I described earlier, the endothelial lining of those capillaries is fenestered, and that has these holes will allow the passage of small molecules, and the basement membrane here is very, very thin and doesn't have much of interstitial space, therefore allowing also the fluids to pass through, also between the filtration slits between the different podocytes. Here is another scanning electron microscopy image of the podocytes, and you can see how compromised that border is, or that barrier is, in allowing the liquid to just swim through. We used to think of that barrier as a static barrier, that we can never change the filtration slits. But now we realize through paracrine talk with the mesangial cells, these barriers are actually dynamic, and the podocytes are capable of increasing those slits or closing them up, and therefore allowing more or less filtration as needed by your body. And we will talk about this mechanism later on. If we run through quickly through the different lining of the cells of the nephron, we will realize that here at the Bowman capsule, or the renal corpuscle, we will have the visceral layer, which is surrounding the capillaries, and then we have the parietal layer, which is outside. The parietal layer, its function is simple, is to contain the fluid that you will be filtrating through. And so it will look like pleural layer, very simple squamous epithelium, and that is very tight together. The tight junctions will be impenetrable because its function really is to collect everything inside here. Now the story is different for the visceral layer, which is formed by what we call the podocytes, and these podocytes, A, they're not sitting completely on the basement membrane, and B, they have gaps in between the cells and each other in what we call the filtration slits. But this is how the cells look like. Then if we go from there into the proximal convoluted tubule, which we will cover in great details, we will realize that they have villi, so immediately you will think that those cells must be specialized to do some kind of reabsorption of fluids. Matter of fact, 60 to 65% of the water becomes reabsorbed at this level, and it does a lot of reabsorption of sodium, potassium, calcium, bicarbonate. A lot of absorption happening, reabsorption happening here, and also excretion. And glucose, by the way, we need to absorb it completely here at the proximal convoluted tubule. Now, in addition to that, because of the functions of these proximal convoluted tubule, you may just immediately realize that you must need a lot of ATP, or energy, for the function of these cells. And how else would we provide the ATP unless we have lots and lots and lots and lots of mitochondria? So you see how the structure of the proximal convoluted tubule suiting very much the function that we need of these cells to reabsorb the matters that you lost through the glomerular filtration, but also to excrete additional matters that you don't need. And we will talk about the tubular excretion in the next few slides. If we go distal from that point, we will realize that the loop of Henle has two different functionally and structurally structurally different, not function, arms and or limbs, and we will call the descending arm or descending limb is the thin one, and the ascending limb will be the thick limb. The descending limb is associated with the uptake of water mainly, and therefore we don't want it to be columnar, we want it to be flattened cells. And why is that? Because the water will depend on the presence of aquaporins, which are specialized canals in the cell membrane, and the water will come in from that side and needs to go out from that side. So we don't want the water to linger around in the cells for too long. So what do? We flatten the cells. There are some evidence suggesting that some sodium reabsorption happens here, but it's not the main site where the reabsorption is happening. At the distal convoluted tubule, you will see, and also at the ascending limb, of which is the thick limb or the thick segment of the loop of Henle, you will see a lot of the reabsorption of the sodium taking place, and also in the distal convoluted tubule. From there we get to the final passage for our filtrate before we can call it urine, and that will be the collecting duct. And in the collecting duct we will have very important two types of cells. We have the principal cells and we have the intercalated cells, and we will talk about the functions of those cells in maintaining your water level and also your potassium and sodium levels, as we will see throughout our lecture. But this is meant to give you an overview of the cell lining of the nephrons and how the cell lining is relating very well to the function of each of those segments in your nephron. Okay, now we will talk about the glomerular filtration. The glomerular filtration, as I said earlier, is guided by the high pressure of blood, which is inside the capillaries. So why do we have high pressure there? Because we move from a very wide arteriole, which is your afferent arteriole, into capillaries. So the pressure is fairly high. It's not like we branched the arteriole into smaller and smaller and smaller branch, so the pressure got lost. No, we went from the afferent arteriole straight into capillaries. So the pressure is high, and to make matter worse, we caused the efferent arteriole to be significantly smaller than the afferent arteriole to make sure that the pressure inside the glomerular capillaries will be high. Now the pressure gradient inside gives you approximately 55 millimeter mercury, which is really the driving force of the filtration. If you want to reduce that filtration, you can have different strategies, but the main strategy, as you will see in a short bit, will be really aiming at reducing the magnitude of your glomerular capillary pressure. How do we do that? By reducing the blood flow in the afferent arteriole, for example. And we'll talk about that when we get into the regulation of the glomerular filtration. But of course we have opposite forces fighting for the water, whether to stay inside the glomerular capillaries or to be filtered outside. The glomerular capillary blood pressure, or the hydrostatic pressure inside the capillaries, is forcing the water outside and the electrolytes to be pushed outside. Now there is another force that would rather drag the water in, and we call that the colloid pressure. the colloid osmotic pressure, which is made by the plasma proteins. Remember, the plasma proteins were not allowed to be filtered outside because they are A, they're big, B, they have a negative charge, which will be repelled by this basement membrane. So we have a force pushing the water outside the glomerulus into the Bowman, outside the glomerular capillaries into the Bowman capsule. And there is a force pulling the water in by the osmotic pressure of the proteins, which are left behind in what we call the colloidal pressure. And third, we have a resistance or pushback by the Bowman capsule, which is a physical pressure mediated by the distension of this Bowman capsule, or as I showed you, or as we discussed at the lecture, it's almost like a balloon fighting back against you blowing air in it. So if you are pushing in liquid here, that Bowman capsule is going to fight back into pushing the water back inside in what we call the Bowman capsule hydrostatic pressure or resistance. The net filtration pressure is if you put the capillary pressure minus the colloid minus the Bowman hydrostatic pressure, then the net filtration pressure is approximately 10. Which is very important to realize because, as you can see, any change in the glomerular capillary blood pressure can indeed result in doubling or halving this amount, reducing it to half, if it is unregulated, which doesn't really take place because, as we agreed in our lecture, that we have a very tight regulation of the pressure in order for us to maintain the filtration at a constant level. And as I told you at the lecture, it's our job to maintain the filtration to be constant, even if your blood pressure increases to 140 instead of 120. And at that level, you don't want your glomerular filtration to triple just because you added additional 20 millimeter mercury. You don't want also your filtration to completely fail if your blood pressure drops by 20 or 30. You want your glomerular filtration to proceed and to continue even if your blood pressure fluctuates up or down. How do we do that? Or what we call the regulation of the glomerular filtration rate. So the glomerular filtration will depend on, as we agreed, mainly on the blood pressure inside the capillaries. And that's something related to the blood pressure and the flow in the afferent arteriole and in the efferent arteriole. In addition to that, we have the colloid pressure, which is fighting against the loss of water. How can that be changed? Well, if you don't have enough proteins, if you have severe anemia, you will have a very high glomerular filtration, and that can result in your inability to pick up glucose and inability to pick up valuable ions like sodium and calcium because you increase the glomerular filtration too much. The final factor we talked about earlier is the resistance of the Bowman capsule, which I showed you earlier in the picture. So the glomerular filtration rate, one more time, is depending on the net filtration pressure, the surface area that's available, and what we call the filtration coefficient. And we used to think that the glomerular surface area is always available and always constant, but then we realized that it's not always constant. We can manipulate which capillaries open and which capillaries close by the mesangial cells. We can also change the shape of the podocytes in allowing the filtration slits to be bigger or less. At the same time, we have the basement membrane, which if there is edema there, or if there is some kind of inflammation in the kidneys, then you will realize that your basement membrane is much thicker, or if there is degeneration of some sort, hyaline degeneration, you will see that the basement membrane is thicker of some sort, and that of course will interfere with your filtration rate. The unregulated influences, which I mentioned earlier, conditions like you lost the colloidal pressure. How do you lose the colloidal pressure? Well, if you are severely anemic or if you have been severely burned, because you are losing a lot of your proteins at that level and the effusion from your burn, and that will increase the glomerular filtration rate because you don't have much of proteins that will fight back for your fluids. If a person is dehydrated, that will result in the blood being too concentrated, and if the blood is too concentrated, then the proteins will have much more osmotic pressure, and the colloidal pressure will win the fight, and therefore the glomerular filtration rate will be reduced. Now, pathologically, you can increase the Bowman capsule hydrostatic pressure. Remember, this is the pressure preventing you to filtrate your effusion or filtrate through from the blood capillaries into the Bowman capsule, and it's the resistance of the Bowman capsule to be stretched by the liquid that you are throwing in or the filtrate that you are pushing in. How does that get changed? Well, if someone has an obstruction of some sort, if someone has a stone or a kink in the urethra, or if someone has a prostate hyperplasia in the male, which results in increasing the pressure in the bladder and consequently in the ureters, and that can lead into increasing the hydrostatic pressure on the retrograde hydrostatic pressure against the filtration, and of course therefore your glomerular filtration rate will be reduced. But these are mainly changed due to pathological situations, and as I told you earlier, the filtration coefficient, which is the available space for the filtration, which whether we are talking about the basement membrane and the thickness of the basement membrane, or how many capillaries are available for the filtration, how many are shut down, and how far are the podocytes away from each other, and how big is the filtration slits. These are things that can be mediated by what we call the mesangial cells through paracrine or myogenic activity of the mesangial cells, and indeed it can change the filtration coefficient of your glomerulus. Now, in addition to that, then we can have changes that can happen that will impact the blood flow into your afferent arteriole and consequently into your capillaries. Well, how does that work? We have two mechanisms. One of them is originated in the kidney and stays in the kidney, and it performs its function in the kidney. And so therefore we refer to this mechanism or this kind of regulation as intrinsic regulation, intrinsic or auto-regulation. And that will prevent spontaneous changes of the glomerular filtration and or fluctuation of the afferent blood flow, and therefore it will maintain sort of constant blood flow in your afferent arteriole, and as a consequence of that you will have semi-constant glomerular filtration rate. So we agreed that this is now the auto-regulation or the intrinsic regulation, and we will realize in the next few slides that we have two components of this auto-regulation. One of them is a myogenic mechanism. Essentially it's from the blood vessels. You stretch a blood vessel, the blood vessel, which is the afferent arteriole in this case, it has smooth muscle fibers, and we agreed before when we talked about the smooth muscle physiology is that the contraction of most of these fibers is myogenic. When it's stretched, it will contract on its own. And when the smooth muscle fibers surrounding the afferent arterioles start to contract, then it will lessen the diameter of the afferent arteriole, and therefore lowering the blood flow getting into the capillary tuft and or in the glomerulus, and therefore lowering the glomerular filtration rate. In addition to that, we will also realize that we have a unique mechanism that's initiated by what we call juxtaglomerular apparatus. Now, the juxtaglomerular apparatus, as you will see in the next few slides and as we talked in the lecture, has specialized cells that are part of the distal convoluted tubule. And we call those cells macula densa. And the macula densa will respond to high level of sodium in the filtrate that escaped the proximal convoluted tubule and escaped the loop of Henle, and now all of a sudden you have high concentration of sodium in the distal convoluted tubule. And so it will talk back to you and will fire back a signal from the macula densa to the juxtaglomerular cells and to the mesangial cells. And the mesangial cells will sense that signal and they will make some modification in the filtration barrier, whether the podocytes change shape or whether some capillaries will shut down and therefore diverting the blood away from being filtrated. But in addition to that, the mesangial cells will talk to what we call the granular cells, which are specialized smooth muscle cells surrounding your afferent arterioles, and it will cause them to constrict. But as you can see, now we have two reasons why those fibers will contract. One of them was the direct pressure inside them, which is maintained by the blood pressure. The rise of blood pressure in the afferent arteriole will result in having this kind of reflex that your smooth muscle fibers will constrict. But the second reason is that you have too much sodium in the distal convoluted tubule. And when you have too much sodium there, it will talk to the mesangial cells, which will talk to the granular cells or the juxtaglomerular cells, and which are smooth muscle fibers surrounding your afferent arteriole, causing those to constrict. Now, those are called autoregulation, as you will learn in the next couple of slides. But in addition to that, you also have regulation that's coming from outside the kidney. And we'll call that intrinsic regulation. And the intrinsic regulation can be sympathetic innervation, or it's because of what we call the reflexes that are coming from whether it's a sympathetic innervation directly to your afferent arteriole, or part of the generalized sympathetic mechanism that is aimed to reduce or increase your glomerular filtration. And we will talk about that in great details as we proceed. So I'm going to skip through this slide since we talked about it at our lecture. But it's a relative summary of how do we adjust the glomerular filtration. For example, here, if the blood pressure goes down, that will be detected by the baroreceptors. That increases the sympathetic activity, and the sympathetic activity will constrict the afferent arterioles through alpha receptors, and that will reduce the glomerular blood pressure, and that would reduce your glomerular filtration rate and the urine volume. And in this way you are conserving the water and you are conserving the salt, and that will increase the blood pressure. So it's a mechanism to correct the blood pressure from dropping significantly. And the other factor, and we will talk about hormones that are secreted by the heart, that's part of the extrinsic regulation, which we have the atrial natriuretic peptide, and we'll talk about that in details in a short bit. First, about the myogenic regulation and the regulation of the blood flow in the afferent arteriole. If I am to cause vasoconstriction in the afferent arteriole, then the blood pressure inside the glomerular capillary pressure will drop. If I drop that, I'm dropping the net filtration pressure, and that will result in the glomerular filtration rate being lower. Now conversely, if I were to dilate the blood vessel, the afferent arteriole, then more capillary blood pressure will exist and more net filtration pressure will exist, and that will result into increasing the glomerular filtration rate. So the glomerular filtration, as we described earlier, it's also influenced by changes in the filtration coefficient, which is the available surface area for filtration to occur. And whether it is the permeability of the glomerular membrane, whether it's how close are the feet of the podocytes to each other, how much capillaries are open, and how many of those are closed by the action of cells that resemble smooth muscle cells, and we call these the mesangial cells that can regulate the passage of blood through those capillaries. So all of these will change the filtration coefficient, and as a result you will have either increase or decrease in your glomerular filtration rate. Granted that the kidney is receiving quite a large amount of your cardiac output, approximately 20 to 25% of the cardiac output, and which is great for you because you want to monitor the concentration of salt, you want to monitor the concentration of water, you want to get rid of all the toxic byproducts. And so it is important for the kidney to get quite a bit of your cardiac output, and therefore the blood supply for the kidney is originating straight from the abdominal aorta, just to make sure that it gets a fair share of the blood passing through. Now, after you have filtrated what we described earlier in the glomerular filtration, it will be up to you to reuptake everything you lost. So consider it that your blood is passing through a sieve or a membrane that everything will go through, everything small enough will go through, the blood cells are held back, the proteins are held back, but everything else is passing through. And as you will realize, this is not an ideal situation where you're losing all your sugar and all your sodium, all your potassium, all your calcium, all your carbonate and or carbonate ion. And so we can't allow that to happen. So there has to be mechanisms through which the kidneys are capable of reabsorbing the electrolytes and the fluids and the nutrients back. In addition, there has to be mechanisms also for the kidneys to actively excrete things that either were not sufficiently eliminated at the glomerular filtration, or they weren't part of the glomerular filtration at all. And that will take place also in the tubular part of your nephron, or what we call active excretion. So the reabsorption happens from your filtrate. This is a simple diagram here telling you that the filtration or the reabsorption will happen across the cells, and in whether it's guided by channels that are open all the time or pumps that are opening and closing, and they require ATP, adenosine triphosphate. What it does is it takes substances and water and ions from your filtrate, dump that into the interstitial fluid, but because of the proximity of the blood vessels to those tubules, it doesn't stay, whatever gets reabsorbed here, it doesn't stay too long in the interstitial fluid, and it's going to be picked up by the endothelium, which now lost a lot of its momentum. Because the pressure here in those capillaries, the peritubular capillaries, is fairly low, about 7 or 8, and compare that to the 55 millimeter mercury capillary pressure that caused the filtration to take place to begin with. So now you drop the filtration pressure or the intracapillary pressure into minimum, and that will allow the water to go in, and that will allow the salt to go in, because the salt concentration here will be much higher than the salt concentration there. And some of you are scratching your heads How can it be that the salt concentration in the interstitial fluid is higher than the plasma? Well, if you remember, the blood here, or the plasma here, has lost all its salt and most of its water. So it's really understandable that the salt, first the water will go in with the colloid pressure, and then the salt will follow, because the salt will say, well, wait a second, we have too much salt here and almost no sodium whatsoever here. So even through the leaky channels we have here, it will just pass through, or in between the endothelial cells, if we have pores, then the salt will pass through these pores to the other side. Okay? So that's in general the tubular reabsorption, how things happen. The reabsorption takes place either passively, whether what we call passive reabsorption, in which no energy is required, and that will be down whether the electrochemical or the osmotic gradients from the area of high concentration, whether it's high concentration of water or high concentration of ions, to the area of low concentration. In addition to that, I have active reabsorption. I have sodium-potassium pump, for example, that will actively pick up sodium from the cell and pumps it into the interstitial space. I have proteins, although they are considered still passive reabsorption. I have proteins on the interstitial side of the tubular cells that have a glucose carrier, and they will be able to bind to the glucose that you reabsorbed in the lumen and dumps that into the interstitial space. And when it's in the interstitial space, it will be picked immediately by your blood vessels. And we will see how some of those mechanisms take place for the active and the passive reabsorption. We'll talk in a short bit in more details about the sodium and the sodium-potassium pump, and how the sodium-potassium pump really is maintaining a steady-state reabsorption of your sodium. And that's an obligatory reabsorption of sodium. You don't regulate this sodium reabsorption. What the cells are really capable of, if we go back to this picture, let me explain it to you. We have the sodium-potassium pumps here, and its function is to take sodium from inside the cell and pumps it into the interstitial fluid. Now the sodium that will be pumped here will be picked immediately by the capillaries. But because I'm pumping sodium away from the cell into the interstitial space, that will create a negative sodium concentration inside the cells. Now we have leaky channels here at the luminal side, or the base of the cell, and that will allow sodium to come in. But the minute the sodium comes into the cell, it will also be pumped by the sodium-potassium pump. So I am causing steady flow of the sodium into this direction, and therefore ensuring that I'm picking at least 90-something% of my sodium from the tubules. Now in the proximal convoluted tubules and the loop of Henle and in the distal convoluted tubule, you don't have hormonal regulation on that, other than the fact that you can regulate the glomerular filtration, and that's it. But you will realize also that in your collecting duct you have additional mechanisms through which you can modulate the absorption or the reabsorption of sodium by a very important hormone called aldosterone. And we will talk about the aldosterone when time comes. But for now, please appreciate the fact about the sodium-potassium pump and its location here, which works into maintaining very low concentration of sodium inside the cell, and therefore it can borrow constantly sodium from the filtrate, and that will go through the cell into the interstitial fluid as we described earlier, and it will be picked by the capillaries, or the peritubular capillaries, or the vasa recta. Okay? Okay. So that explains to you what happens with the sodium here, and why is it moving from the lumen into the interstitial space and consequently into your blood. And the question is now, what about chloride? Well, chloride has a negative charge, and so it will follow sodium, so they'll do other things. We have the carbonate also follows sodium because the carbonate has a negative charge. But in addition to that, now you're creating salt inside the interstitial space, and that will create higher osmotic pressure inside that interstitial space, which will be capable of absorbing water. So water is not really transported by an active mechanism. It just goes back its own concentration gradient from the area of low salt to the area of higher salt concentration, relative salt concentration, of course. Okay, so here's what I was telling you about the sodium-potassium pump. What it's doing is it's pumping the sodium from the inside of the cell into the interstitial space, and that will be picked by the blood. That creates a low sodium concentration here, and that will take in sodium from the lumen through the channels or the co-transport. We're saying here co-transport because many of those channels don't only carry sodium, but together with sodium they will pick something else, like chloride or chloride potassium carbonate or glucose or amino acids. All of these are what we call co-transport carriers or symports that will allow other substances to go in the cell in addition to sodium itself. Therefore, the passage of sodium from the lumen into the cells facilitates also the passage of other substances like amino acids, like glucose, like potassium carbonate, chloride. All of these will go through the same port as sodium. Brings us now into a very important mechanism which we talked about earlier, which is the renin-angiotensin mechanism. Before we go into any deeper into the reabsorption of fluids, let's pause for a second at this level. And let's appreciate the fact that now we have a glomerular filtration that happened. We agreed about the regulation of the glomerular filtration by intrinsic and extrinsic mechanisms. But there has to be mechanisms also designed to regulate the glomerular filtration beyond that. And one of them is the renin-angiotensin system. Well, what the renin-angiotensin system does, renin-angiotensin-aldosterone system, what does it do? It will be stimulated by high sodium concentration in the filtrate at the level of the distal convoluted tubule. So the distal convoluted tubule is telling you that you have passed too much sodium through, that all these mechanisms that were designed to pick up the sodium did not pick it completely, or at least too much sodium is still passing through the distal convoluted tubule. So it's telling you, slow down, and I compare that with you to Charlie Chaplin in modern ages or modern eras, where he was not able to maintain with the assembly line, and because the glomerular filtration rate now is too high, then your tubules are not able to reabsorb the sodium. And these cells, we agreed, it's called macula densa, that have sensors for sodium. And they will talk back to the mesangial cells, and the mesangial cells will talk to the granular cells. Now the granular cells are granulated because they have an enzyme in these vesicles called renin. And when the renin is being released from the mesangial cells into the capillaries, that will cause the cleavage of a prohormone called angiotensinogen. That is secreted by the liver. It's a protein, it's a big protein. When you cut a part of it, it will activate it and will make it angiotensin 1. And the angiotensin 1, as you will see, can be converted into angiotensin 2. Now what does angiotensin itself do? From its name, angiotensin, it causes tension in the blood vessels or vasoconstriction. So this is one. Angiotensin is also capable of stimulating the thirst. So we'll tell you you're losing too much water and your blood pressure is going down, so why don't you take some water? It will also stimulate your collecting ducts to pick up sodium. And when you pick up sodium, then as a consequence, you will be retaining water, and therefore your blood pressure will be elevated. And they will stimulate the release of another hormone called antidiuretic hormone from the hypothalamus. the stimulation of the antidiuretic hormone will allow you to conserve water at the level also of the collecting duct by creating more channels called aquaporin that will be holding the water in from the filtrate, and therefore your urine will be highly concentrated. All of these functions are the functions of angiotensin II. In addition, angiotensin II will also stimulate aldosterone, and aldosterone is a hormone that's produced by your suprarenal cortex, and it will also work, aldosterone will also work on these receptors in the collecting duct into keeping your sodium, and when you keep the sodium, then indeed you're keeping water, because your osmotic pressure will rise unless you retain water as well. Okay, so this is the renin angiotensin aldosterone system, and you will see now in greater details in the next few slides how the renin angiotensin system works, how it's activated, and what does it do. Okay, so anatomy wise, or the cellular compartments of the renin angiotensin system, renin angiotensin aldosterone system, is these cells, the macula densa cells, which are modified cells of the distal convoluted tubule. Now these cells, if they sense too much sodium, they will talk to the mesangial cells, and the mesangial cells will talk to these cells, which are the granular cells or juxtaglomerular cells. And these guys will fire renin, and renin, as we talked, it will be able to cleave angiotensinogen into angiotensin I. This is another picture depicting the same thing as I told you earlier. We have here the macula densa. The macula densa will talk to the mesangial cells. The mesangial cells will be talking to these cells, which we call the granular cells, or juxtamedullary cells. And these cells will be able to secrete renin to you. So here what happens. You are secreting renin from the kidney. Renin will cleave angiotensinogen into angiotensin I. And in the lung, mainly in the lung, we have an enzyme called ACE, angiotensinogen converting enzyme. And we have some also in the kidney, which will convert angiotensin I into angiotensin II. Angiotensin II will cause vasoconstriction, stimulates aldosterone secretion, increases antidiuretic hormone secretion, increases thirst, but it also speaks to your collecting tubules to retain more sodium. So one more time, angiotensinogen is cleaved by renin. That will give you angiotensin I, and that by the conversion of ACE, which is mainly present in the lung, but to some extent we discovered it also in the kidneys, that will be made into angiotensin II. The function of angiotensin II, vasoconstriction, stimulating the reabsorption of sodium either directly or indirectly through aldosterone. Then 3 will stimulate the hypothalamus to release antidiuretic hormone, and that activates and also activates the thirst center directly and indirectly by the antidiuretic hormone. Angiotensin II will constrict the afferent arterioles, and when you constrict the afferent arterioles, then you are reducing the glomerular filtration. And it will cause the mesangial cells to contract, and therefore you have lesser of a filtration membrane available for the glomerular filtration to occur. All of this is happening because of the angiotensin II. Now, what stimulates the angiotensin, the renin secretion? What stimulates the renin secretion is if I would reduce the stretch of the afferent arteriole into below the mean arterial pressure, becoming lower than 80 millimeter mercury. What that tells you is that your blood pressure dropped, and it's not a good time now to filtrate too much liquid and to lose your valuable fluids and your valuable sodium. Remember, when you go to the ER, when you are subjected to a shock or when you have lost blood, the first thing they put into your arteries is a solution that has water and sodium chloride. Sodium, it's very, very important for you. So you don't want, when you have a situation of low blood pressure, to start even losing more. So in that sense, when your blood pressure goes fairly down, then you want to stimulate the renin, and the renin, as you saw, it does its work through the activation of angiotensinogen, and finally you get into angiotensin II. It can also be stimulated by the macula densa cells. Remember the macula densa cells? These are specialized cells in the distal convoluted tubule. They will sense that you have too much sodium in that filtrate that passed through the distal convoluted tubule, and will tell you slow down your filtration. You will slow down the filtration A by regulating the glomerular filtration, either directly by causing constriction of the afferent arteriole, or in the long term by causing these same cells to... So the stimulation of the granular cells by the macula densa will result in the release of renin, but at the same time you're also constricting the smooth muscle fibers that are surrounding the afferent arteriole, and therefore you're reducing the glomerular filtration. Thirdly, if the granular cells are stimulated by adrenergic receptors, by sympathetic stimulation. And when will you have sympathetic stimulation? If your blood pressure drops, or if you are in a situation where you want to conserve your fluids. And that will result into the stimulation of the granular cells. And as we discussed earlier, when you stimulate the granular cells, then you are liberating renin, and you know the rest of the story, how the renin acts on the angiotensinogen and the results of that mechanism. Okay. We have an opposite mechanism that works in a reverse way, which is secreted by the left atrium. It's a hormone, if you remember, from the cardiovascular system. We have the atrial natriuretic peptide, and that will sense too much tension on the heart muscle. And they will secrete to you this important peptide, which we call atrial natriuretic peptide. And that will go, and the main function of the atrial natriuretic peptide will prevent the reabsorption of sodium from the distal part of the nephron, mainly from your collecting duct. So atrial natriuretic peptide will work in an opposite order to that of the aldosterone. Okay? So, and the aldosterone, both aldosterone and atrial natriuretic peptide, we will have ample of opportunity to talk about that when we get into our endocrine chapter. So we did discuss the reabsorption of ions, of water, of nutritional components such as glucose and amino acids. Proteins will be taken in by endocytosis. Amino acids and glucose will be following sodium by the means of specific channels that will carriers that will carry both sodium and glucose, or amino acids, or chloride, or not chloride, but carbonate, and so forth. We also have antiports that will take in sodium but will kick out in exchange hydrogen, because both of them have a single positive charge. So you can take in one sodium ion and throw away one hydrogen ion in exchange. So if we are to consider the reabsorption, again you think of an assembly line. In the assembly line, it's limited to the speed at which the products are passing through the people standing at the assembly line. And you can imagine what happens to them if the flow goes extremely high. They're not going to be able to pick it up. So if the flow of glucose, for example, is passing too rapid and too much, the quantity is too much for the same amount of workers to pick it up. And remember, there is no regulatory mechanism inside the kidney to increase the reabsorption of sodium. The reabsorption of sodium has what we call tubular maximum, or TM for short. That's an important word to learn, tubular maximum. And the tubular maximum for glucose is a certain level, and if you exceed that level, then you will start seeing glucose in the urine. And that's really what happens when someone is suffering from diabetes mellitus. where the glucose level in the blood is starting to become too high. And when you have too high blood level of glucose, that will be in the blood, in the amount of glucose that is filtrated. And definitely the tubules are not capable of dealing with this high level. Then you start to see the glucose being excreted in the urine, as you can see here. Okay, because you are essentially unable to cope with the high levels of glucose that you started to see in the tubules. And now, of course, glucose has its own osmotic pressure, and if you are not picking up all the glucose, then you start to see higher and higher amount of urine being formed, and that's what we call polyuria, which is one of the symptoms for people who are diabetics, is to have plenty of urine. So again, here I'm gonna summarize in the next 3-4 slides about the reabsorption of what we saw so far. We agreed that the filtrate here, at the filtrate level, we are losing essentially everything except for the cells and the big proteins and some fluid that will be maintained here, but it's not much. Now the sodium and the water will be retaken, and we agreed that the mechanism how we retake the sodium by sodium-potassium pump that's situated on this side and creating a negative concentration inside the cells, which would be here, and you will see that in the next slide. And therefore the sodium is being pumped from the tubules into the interstitial space, and from the interstitial space to the blood capillaries, or the peritubular capillaries, or the vasa recta. And at the same time, water will also follow, because water likes to follow sodium. And what it doesn't show here is also something like the chloride, which will follow sodium, and other things which we will see in the next few slides. So here are some things that some of the substances that undergo reabsorption in the proximal convoluted tubule, as we discussed at the lecture. So here is a mechanism through which you are reabsorbing sodium. Let's start here. We have sodium-potassium pump, which is picking sodium, creating a low concentration of sodium here. Sodium comes in from the lumen, but instead of coming by itself, it also picks glucose as a hitchhiker with it through the same channel, or the co-transport. And the glucose now being accumulated inside, it will be helped to the interstitial space by a carrier, or facilitated diffusion here, and that will allow glucose to be in the interstitial fluid, and that will be picked up by the capillaries. So this is a mechanism through which the sodium is being picked up. Here's again, we have the sodium-potassium pump allowing low concentration of sodium here. When you have low sodium concentration, you will start to receive sodium from outside. But this time it doesn't come alone, it comes in exchange, not together with, in exchange for hydrogen, because hydrogen also have a positive charge. So you get sodium in and you kick hydrogen out. This is not an active transport, this is an antiport. And now the hydrogen that is being kicked out, you will see later on that it's very, very important for you, because it helps the recreation of carbonate, and we will see that in the next slide here. So this is the part we saw earlier, which is the sodium exchanging with hydrogen, and now we have hydrogen being here in the luminal space. But let's look at this. What else passed through the glomerular filtration? HCO3. Unfortunately, we don't have any specific channel for HCO3 here. So what do? Remember the hydrogen that was exchanged? That hydrogen will combine with the HCO3, forming H2CO3. H2CO3 will split, giving you hydrogen, or giving you water and carbon dioxide. Carbon dioxide likes to go back into the cells by diffusion. That's one of the things that pass through the cell membrane without the need for any channel or carrier or anything. So carbon dioxide goes in. Inside the cell I have carbonic anhydrase, and the carbonic anhydrase will take carbon dioxide and water and will form HCO3 and hydrogen ion. The hydrogen ion will go out again to continue the same thing we talked about earlier. The HCO3 has a channel here which goes from the cell to the interstitial space, and from the interstitial space to the capillary space. Okay? So again, another summary here where we have a symport for sodium, glucose, amino acid, phosphate. All of these guys can be symported or co-transported by the same protein from the luminal side. We have an antiport, which I talked about earlier, for sodium, bringing sodium in and kicking hydrogen out. And we have an exchange mechanism for bases, which are metabolic waste or other kind of bases with a negative charge, in exchange for chloride, which I need to my body. Water will follow in because the sodium is flowing in, the glucose is flowing in, the amino acids are flowing in. All of these guys are creating a higher osmotic pressure here. So the water will start moving through aquaporins from this space, into the intracellular space. Now, in addition to that, I have the sodium-potassium pump pumping the sodium here, and the potassium is actually carried by another channel with the chloride. That's a symport. You don't have to remember that part. And the sodium and the carbonate are being carried also into the interstitial space. That creates high osmotic pressure here, along with the glucose and the amino acids, and therefore the water will also follow. Now, not all the transport has to occur through the cells. Few of them can pass in between the cells, like sodium chloride and water can happen in between the cellular spaces. Okay, again, here is another summary for the things we covered with the sodium and the other ions, and in addition the water also reabsorption. So we learned about the reabsorption, but we did not talk about the opposite way, the excretion. Now, there are things that are excreted or they are filtered through in the glomerular filtration. But that's not enough, and sometimes they get reabsorbed again, like the potassium gets reabsorbed again, and it will be up to us to excrete it. Hydrogen, we need hydrogen ion, we need to excrete that, or else we will end up with acidosis. There are certain things much bigger than passing through the glomerular filtration, and we want them to be excreted elsewhere, especially the negatively charged ones. Why? Because in the glomerular capillaries we have the basement membrane, which doesn't like to allow things with negative charge to pass. So we need to start excreting things, and we have certain substances that we can use to measure the renal excretion. Something like it's called HAP or PAH. I think it's PAH, which is aminohippuric acid, and phosphoaminohippuric acid, if I remember correctly. And that is a drug that we can give in, and will give us the summary of the glomerular filtration, as well as the kidney's ability to excrete. That's one of the things that gets excreted. Urea is also excreted, although it gets reabsorbed, and it's a sort of tricky. It gets first filtrated, and then 50% is reabsorbed in the proximal convoluted tubule, and then the remaining 50% will be reabsorbed, and really the active excretion of urea happens in the collecting duct, and we will talk about that when we get to it. So the most important things that we need to get rid of is the hydrogen ion, the potassium, and the organic ions, and these are secreted only in the proximal convoluted tubule. What's not showing you here is the urea, which is secreted mainly by the collecting duct. Okay? So this is an interesting slide, and I'm going to finish the first part of this lecture with this slide, where it's showing you what got reabsorbed at the proximal convoluted tubule, and what got actively secreted at the proximal convoluted tubule, and compare that to what got reabsorbed and secreted at the distal convoluted tubule, as well as the collecting duct. So I'm going to stop here, and I am going to continue with the second part for this lecture in the next video, and so we'll see you there, and I hope you find this video helpful and useful for your review process to prepare for the exam. Have a good day and see you in the next video.